Hey everyone, here's another video on chapter 9, section 3, which is two means, independent samples. So the first thing we're going to talk about is just kind of a review of independent and dependent samples before we jump into how we construct confidence intervals and how we do hypothesis tests for two population means. In part 1, we'll discuss situations in which the standard deviation of the two populations are unknown and not are assumed to be equal. This is more commonly the case that we'll have. In part 2, we'll discuss briefly the two other situations. The two population standard deviations are both known. And secondly, possibility the two population standard deviations are unknown, but are assumed to be equal. Again, in typical fashion, part 1 is usually the way that you want to proceed, where you don't know anything about the two population standard deviations, and you're not assuming anything about them. Part 1, we have independent samples. The standard deviations unknown, right? That's what sigma 1 and sigma 2 are, right? And not assumed equal. So a review of independent and dependent, right? Two samples are independent if the sample values selected from one population are not related to or somehow paired or matched with sample values from the other population. Samples that are dependent, you can think of usually as something like paired data, such as maybe before and afters, or husband and wife, or in some other fashion that relates them. A reminder of what independent and dependent means. So here's a couple of examples. So for example, researchers investigate the reliability of a test assessment on a group consisting of 30 students who took proctored tests, and a second group consisting of 32 students who took online tests without a proctor. The two samples are independent because the subjects were not matched or paired in any way. And we're going to assume that those 30 students are different than the 32 students in the other grouping. An example of dependent could be husband and wife. And a lot of times you might think that the husband is taller than the wife. And that could be the case. And this is where we could do this type of test if we wanted to. But this is an example, though, of paired data, or basically dependent samples, right? They depend upon each other. There's some type of relationship between them. So some notation you want to be familiar with. Mu1 is the population mean. Sigma 1 is the population standard deviation. N1 is the size of the first sample. And X1 bar is the sample mean. And S1 is the sample standard deviation. Again, these are all, with the ones are for basically sample 1 or the one from population 1. You'll also have the same corresponding notation if you have population 2. The only thing that changes is instead of 1, this becomes 2. That's the main defining thing. And these notation you should feel pretty comfortable with as you've seen them throughout the text. So some of the requirements first before we can proceed. Sigma 1 and sigma 2 are unknown and we have no assumption made about them and whether they're equal or anything like that. 2, the two samples are independent of each other. 3, both samples are simple random samples. And 4, we have an either or clause, which means that either two sample sizes are both large, over 30, or both samples come from populations having normal distributions. So you can either have either or you can have both of those. But either way, one of those requirements must be met. Now the hypothesis test for two means, independent samples. Basically, this is a student t-test, right? You guys know because there's a t-stat right here. And now we have x1 bar minus x2 bar, and minus mu1 minus mu2. And then we have divided by the square root of s1 squared divided by n1 plus s2 squared divided by n2, right? Again, remember S is the sample standard deviation, and if you square it, it's actually the sample variance, okay? So where mu1 minus mu2 is often assumed to be 0, because in the null hypothesis, we have mu1 equals mu2. And again, you can just rearrange that and have it be mu1 minus mu2 equals 0. And that's how we can say that this part right here is generally 0 unless otherwise specified. So for the hypothesis test, because we're using the student t-distribution, we need to know the degrees of freedom. And so in this book, they use a conservative estimate, and they just pick whichever is the smaller of the degrees of freedom. So in other words, say N1 was 20 and N2 was 11. So 20 minus 1 is 19, and 11 minus 1 is 10. Well, degrees of freedom of 10 is the smaller one, and that's the one they would use because it's more conservative estimate. If you use technology, it would be a little different. P-values, you can refer to your table, the student t-distribution student T distribution table, or you can use basically technology to find that for you. And then we have critical values, refer to your table as well. Confidence interval estimates of mu1 minus mu2, independent samples. So we have x1 bar minus x2 bar minus the margin of error is less than the population mean from population 1 minus the population mean from population 2, which is less than the sample mean minus the sample mean from population 2 plus the margin of error. And you can see the margin of error, again, is calculated with T alpha over 2 using the student T distribution. And alpha you might be picking however you want your confidence interval. And then the degrees of freedom is whichever the smallest is of the two sample sizes minus 1. So a note of caution, before conducting a hypothesis test, consider the context of the data, the source of the data, the sampling method, and finally explore the data with graphs and descriptive statistics. Basically, be very sure to verify that the requirements are satisfied before you go down this road, okay? So here's an example where basically they have two groups, subjects. One is given a red background group, and they're asked to think of creative topics to use with a brick. The other subjects were given a blue background group where they were given the same task, and their responses were given to a panel of judges who then scored them on their creativity. Researchers make the claim, though, that blue enhances performance on creative tasks. Test the claim using a 0.01 significance level. All right, so we got to make sure the requirement checks are made. The value of the two population standard deviations are unknown and we're assumed not equal. All right. Two, the subject groups are independent. Yep, you have the red group and the blue group. The samples are simple random samples, and both sample sizes exceed 30. So if we're looking at the data that we have, sample sizes are greater than 30. We have their mean scores. This is their creative score, right? And then we have their standard deviations. If you were looking at this data in general now, though, you should see that their sample standard deviations are quite a bit different. In fact, this has got more variation in it, and this has less variation in it. You also see that this has a higher score than this one, but it doesn't necessarily mean they have overall higher scores, right? Because the standard deviation is quite high here, whereas a little bit lower. When we go through a hypothesis test, we're doing the 8 steps that we have outlined. The first one is to take the claim and write it in symbolic form. So the claim is that blue enhances performance on creative tasks. So in other words, group 2, which is the blue group, has a mean score that's greater than group 1. In other words, mu1 is less than mu2, or you could think of it as mu2 is greater than mu1. Generally speaking, though, you always want to write the first group first and the second group second. Okay? If the original claim is false, then write mu1 is greater than equal to mu2, and then therefore we can write our hypothesis. And basically equals in the null, and the alternative, we have our claim, which is that mu1 is less than mu2. In other words, the red background group has a lower mean score than the blue background group. And then step 4 is to pick the significance level. And I think we picked 0.01, but we have 0.05 here. So step 5, because we have 2 independent samples and we are testing a claim about a 2 population means, we use a T distribution. So we calculate that test statistic. And again, you might be wondering, why is mu1 minus mu2 equal to 0? Well, that's because, right, the null hypothesis mu1 equals mu2, we minus this over to the other side, equals 0. And that's how we get this part to be 0. We plug in everything else we know, we'll get a t-stat of negative 2.979. And if we go back up here, because this points to the left, we know that's a left-tailed test. So we can do the critical value method, where we find basically a critical value that cuts off that 0.01 from the 0.999. And we see that our t-stat, or our test statistic, lies to the left of that distribution, which is in the the null hypothesis region, or we might call it the rejection region. So because the test statistic does fall in the critical region, we reject the null hypothesis. So the p-value method would also indicate this as well. In fact, we have a p-value of 0.0021. And even if we're using 0.05, we still reject. But even if we're using 0.01, which is even narrower, we still reject the null hypothesis. Now, in step 8, right, we got to always reword this back to the original claim. So you might say that there is sufficient evidence to support the claim that red background group has a lower mean creative score than the blue background group. I think that seems kind of obvious, right? You might also be biasing your study in some extent. Let's go back a second. You might be biasing your study, right? If you're giving them a red background group and a blue background group. I think a lot of us would think bricks are usually red, right? So I think that's kind of the bias that you might be making. Using the data from the color creative example, construct a 98% confidence interval estimate for the difference between the mean creative score for those with a red background and a mean creative score for those with a blue background. So we got to get our basically margin of error. So our T alpha over 2. You notice this 2.441 is basically our critical value. And then we'll put in our calculations and we'll get our margin of error. And we'll basically subtract that from our sample mean minus our mean 2. Right? So in other words, this minus this is going to be a negative number. Minus that's going to give us even more of a negative number. And over here, we're going to add that on. But that'll still give us a negative number. And if you're thinking about this, the null hypothesis, which is mu1 minus mu2 equals 0, 0 does not fall within this confidence interval, and therefore we would reject the null hypothesis. So we'd actually have the same conclusion as we had before. So it does not contain the value of 0. So this suggests that there is a significant difference between the two means. Now, part 2 is the alternative methods. So these methods are rarely used in practice because the underlying assumptions are usually not met. So the first one is that the two population standard deviations are both known, and the test statistic will be a Z instead of a T test, okay? So in other words, instead of using the student T distribution, we'll use the standard normal if we know the two population standard deviations. Again, this is very rare that this is actually true. 2, the two population standard deviations are unknown, but we assume they are equal. So we pool the sample variances. Again, part 1 is the more common applications. Part 2 is something that could happen, but you'd have to know more specifically if it would be the case. Likely it's not. So hypothesis test for 2 means independent samples with the standard deviation from group 1 and standard deviation from group 2 known. So again, we'd use the standard normal distribution, and then down here, instead of using S, we have sigma. Okay? And same methods as we've done before. Confidence interval, the only things that would change is that we use Z alpha over 2 instead of T alpha over 2. And instead of S1 squared, in other words, the sample variance squared, oh, sorry, not the sample variance squared, the sample variance, we would actually have the population variance for group 1 and then the population variance for group 2. Now, if we're assuming they are equal, which is the second scenario of part 2, that means we're going to pool their variances. So this is how we calculate the pooled variance. So the sample size minus 1 times the sample variance of group 1 plus the sample size of group 2 minus 1 times the sample variance of group 2 divided by basically the total groups added together minus 2, which is the same thing as how you find the degrees of freedom. And this again, we're using a student T distribution when we assume they're equal, but we don't know their values. And again, confidence interval, same steps. The only thing that changes is whether we're using T alpha over 2 or Z alpha over 2, and then the pooled variance. So part 2, the alternative methods. So this is kind of a added advice, if you will, but basically adhere to the recommendations of the homogeneity of variance in the 2 sample mean tests by Moser and Stevens. So assume that sigma 1 and sigma 2 are unknown, and do not assume they're equal as the bottom lines of what their test showed. So in other words, use the techniques described in part 1 for most of chapter 9, unless you are specifically stated to do otherwise. So methods for inferences about 2 independent means. First thing is, do we know sigma 1 and sigma 2? No. Can we assume they're equal? No. Then this is the best way. This is the most common way that we'll do it. If, though, they are known, we'll go with the standard normal distribution. This case almost never occurs in reality, okay? All right, so if we don't know them, but we assume they're equal, then we'll use a pooled standard error. Some statisticians recommend against this approach. So a lot of people recommend this last way, where basically you know nothing about them, you don't assume anything about them, and you go through and test it that way. That's generally how people would look at it. And now we're on 9.4. Again, if you have questions, please let me know. I'll be happy to help you out.